if you want this or not. Okay. Share the. Okay. And you should see my screen now. And probably hear the kids in the background. Okay, so let's wait a second. Okay, the last ones are in. One more joining. Okay. Thank you for coming and joining the first Rust and Tell in Halifax. I just talked to the speakers, and actually none of them is in Halifax, but they're close enough. So let's call this an East Coast Canada meetup. I think I have to pick a city because maybe this attracts a few folks. But I'm very happy that we found a few speakers, that we found a few participants to join today. And my name is Bastian. You can find me on Twitter. I'm not really active these days, but in case you want to have talk ideas or share some things, I mostly see it once a week or twice a week. So if you have any talk ideas or other things you want to share, feel free to contact me on Twitter or on the Meetup platform. I'm a full-time Rust programmer for the past around 5 years. I also wrote a book called Rust Web Development with Manning. So I'm pretty into Rust for the past 5 years. And I did host the Rust and Tell Berlin meetup also for the past 5 years. Oh, great. And you have the book. I saw that Michael has the book. Great. You will always have a fixed spot now at the speaker slot. Yeah, so I'm happy to bring Rust people, yeah, bring all the Rust people together, and the idea is basically to share just your journey, with the rank. So with the language or your projects around the language. This is not meant to be that just people with the proper skills, proper projects and big backgrounds can share their talks here. It's more about a group who can share their experiences, little hacks, you can share one line of code and talk about it for 20 minutes. It could be that you're just curious about the language. The only thing I would say is we want to see some code, it should be 2 lines of code, 1 line of code, but it's not just a talk about an idea or to sell a project. It's about a hack, some coding challenge, some project. Feel free to, for example, show your advent of code in Rust or something like this. And it's also a great place to connect with like-minded people and have some, sort of some networking experience or networking opportunity. We generally, so this I copied from the Berlin meetup, but their code of conduct is pretty solid. So I always said at the previous meetups that we all share our free time here. We want to be nice. We want to be welcoming. The whole Rust community is pretty open, pretty welcoming, and I want to carry this over in every meetup we have. So please get out of your way to make feel people, I don't know, welcome and comfortable just being here. It's a bit harder and also easier on Zoom, but maybe there is an in-person meetup at some point. So I just want to highlight that people come here and spend their free time to show their projects. And I just want to have that people have a great time here. And the concept is like this. Oh, I didn't remove the catering. We don't have catering today. I'm sorry. And I didn't change even the name on the slides. Oh my God. So this is like the Rust Intel Halifax. We have three speakers. We will have a break after the second speaker. I'm not sure of how much break we need because people are mostly in their home. They can maybe pause. So like it just gives people a chance to maybe go to the like bathroom or grab something to drink. But I will probably like make this breaks in between talks, maybe quite short, maybe 5 minutes. After each talk, there's like a little question round, and then we hand over to the next talk. Yeah. So like in this concept, I haven't tried yet like a hangout after the meetup. I had it once during the pandemic that we had like breakout rooms so people could chat, but then I found out that most people drop out after the second talk because it just was too much time to spend. So I will ease it in a little bit here and say like we don't have like a dedicated hangout time here. Like we have the three talks, we have the questions, and then for the next meetup, I have to think about a different concept of how to bring in these breakout rooms, but to keep the time a bit like manageable and the attention span as well. We have the three talks and that's it. And I was quite excited to actually have those three speakers. It doesn't seem like a lot, but like the speaker said, what makes these meetups actually like valuable and happen. So I'm like very thankful for like Michael, Josh, and Alex to have taken the time to prepare a talk and to show up and to give a talk, and also for the participants to show up and like make this a meetup. So I just click a few buttons on like the meetup platform, but you folks actually bring in the time and bring like the valuable stuff in. So I'm very grateful for this, and feel free, like if you're like not a speaker today, feel free just to get in touch with me, bring in an idea, like yeah, like for a talk, and I'm happy to help out with forming this into a proper talk. And the three talks we have today spans all sorts of things from like embedded programming in Rust to category theory in Rust, all the way to how to have graphics in Rust. So like it's a full stack meetup today. We have something for each one of us. Okay, and with this being said, thank you so much for joining today. And our first talk is, I think it was is Alex who starts, and then it's Michael, and then it's Josh. So feel free to share your screen and take it away.
Okay, thank you very much. Okay, I hope you all can see my screen. My name is Alexander. I'm living in Germany, so far away from Nova Scotia, but I'm somehow related to Nova Scotia because part of my family is living there, and I'm happy to be here with you tonight. I want to talk about yeah embedded development with Rust. I'm a complete beginner in this topic, and I want to share my learning steps, my learning experience so far. So it all began when, in the past holiday seasons, when I had a little bit too much free time, and I wanted to find out more about microcontrollers and what is it all about, because they are everywhere, they are ubiquitous as core of embedded systems. They play an important role in our daily life, even if we don't notice, if I didn't notice. They control the real world with sensors and actuators. This is so they are controlling, taking measurements from sensors and actuating something in the real world by actuators. And Yeah, so far they are mostly driven by software written in C and C++, which I found very scary given the importance of these small systems. But the same applies to operating systems as well that are mostly written in C, C++. Yeah, so we need to change that, or I need to change that, I was thinking, and so I started just a bit about the advantages of embedded systems compared to complete computers. They are, well, they are very basic. They have low power consumption, low cost, high responsiveness that's the real time aspect. Yeah, a Linux system, if you want something from the Linux system, the Linux system can decide, no, I first have to swap my memory and then I can handle what you are requesting from me. But the embedded systems, they don't have an operating system, so everything is very direct and real time. And because there are less moving parts, there is a higher reliability. So now why Rust in this case? As always, that's the memory safety compared to C, C++. The borrow checker guarantees a memory safety, while that you don't have in C. Explicit integer conversion and overflow. It was something that yeah, that I noticed on my path that when I compared driver software written in C to the driver software written in Rust, that yeah, in C a lot of implicit integer conversion happens, and you as a developer have to know the rules and work with it. And in Rust it is explicit. Zero cost abstractions. Yeah, we all know that there are it is a modern way of programming in Rust, and all this gets optimized away, and the resulting executable is then small enough and suitable for even these small embedded systems, so that there's really zero cost with connected to these abstractions. We have a modern native build system, Cargo, and package management is, yeah, on over crates.io. I can pull in every crate very easily, and that's yeah, there is nothing comparable to that in C, in the C world. So now I started with the learning material given by the Rust community. There is the discovery book, which is yeah, it's a Rust book about the first steps in the embedded Rust development world. And the text in this book, it works with a microbit hardware. The microbit is a small development board, and it is yeah, intended for educational purposes for school. And while I was starting reading it, I noticed that this microbit is actually similar to that we had in the house, because I bought that one for my child when it was in elementary school. So the same display, the same LED matrix. So I was giving it a try, and the first steps even worked without any adaptation. So yeah, I was actually then doing all these examples in the book on the different hardware, but which was similar enough so that I could make it work. And the goal in the end was for me was to implement the electronic compass from chapter 9 of this discovery book. The Calliope Mini is a development board for school education. It's a German thing, I think. It's popular in German schools, and yeah, everything is. I don't think it is even known in other countries. It is not a toy, however. There's it's the hardware on it, the chips and the components are they are found everywhere in other embedded systems as well. And my version is outdated, but that doesn't hinder learning or trying to learn with it. That was completely okay. So there are way too many details on this slide, but it's just about the MCU is the core of the embedded system. This is the microcontroller unit. It's a complete system on a chip, and it has a processor, flash memory, which is the equivalent to hard disk. It's non-volatile memory, and a RAM, of course, in very small numbers, and still other devices on a single chip on such a small black square. And this MCU sits on a board on the Calliope Mini board. For example, there are, apart from the MCU, there's the LED matrix. We have seen it. We have a USB connector with real-time transfer debugging module, and this part is usually there with development boards. Other embedded systems, of course, they don't have this device on board because you need it only during development. And yes, and there is another device on it, on the board. This is accelerometer, gyroscope, and magnetometer sensor. And this is that peripheral that we need for the compass that we want to implement. So just a view on the Rust embedded ecosystem. I had to find my way to systemize all these different parts. There is a very basic layer, the peripheral access crate, and then the hardware abstraction layer, which is also specific to the MCU that you are dealing with. And then hopefully there's a board support crate for the board you're working with. In my case, there is one for the microbit, and I could derive from that one, with a few adaptations, one for the board I was working with, the Calliope Mini. The centerpiece of this ecosystem is the embedded hull crate. This is unifying abstractions for all of the different MCUs that are supported, and this is conceptually speaking the interface that all the specific hulls are implemented against. So, and the hull driver for the sensor is that one that I had to implement myself, because the microbit board did use a different compass sensor. And this hull driver is dependent only on the embedded hull and not on the specific hull of this MCU so that it will work with different MCUs. I can show this in a diagram. maybe better. So we have the embedded hull, and these are the specific implementations of the MCU support software, and this is the board support crate, and which is dependent also on the hull, and this is the hull driver, which is only dependent on the embedded hull crate. So no matter what MCU you are using, you could use this driver for your project. And your project basically would depend only on the board support crate and the sensor driver. This is where my example, my demo program in the end, this compass program is dependent only on the board support crate and the sensor driver. So let's have a look at the program. I just want to highlight three particularities. It's a no STD environment. That means you don't have, of course, no STD because you don't have an operating system and no standard lib. So you don't have an allocator. It is a no main environment. That means you don't have the usual main entry function, but you can annotate your own function that will serve as an entry function, and this function will not return. It will end in it will be in an endless loop. So this is basically what is then running on the embedded system. So let's have a look how this is then, how it looks. Okay, yeah, we have seen here the no main, no STD. And this is this name is arbitrary. It could be named in other ways, this function, but it is marked as the entry point, and it ends with this loop that is endless. It will never return. That's why the type is never here. The return type is never of this function. So, and this will basically read the magnetic field data, will calibrate it. This is an important step, that otherwise there is always an offset in the measurement data, and then turn it into a direction, and this direction is displayed on the LED matrix as an arrow. So I will later have you a look at that. It is very comfortably built because you can build a binary with just one single command with a cargo embed, and this will build the binary and flash it to the board. So this is all the whole development system is contained in this as a cargo extension. When we are using the compass, then first there will be a calibration step. This is to make this this calibration possible, to take away the offsets in the measurements, and then there is an arrow is displayed, and this arrow points then north. Hopefully, can you see now in my camera? I'm holding that device with an arrow, and because you have to trust me that this is north, but I will show you that when I come with a magnet, okay, this seems to be the south pole of the magnet. I turn around the magnet, and then the arrow should follow the magnet when I move it around. So this spectacular result. Yeah, just a few words because this HAL driver, because this was the main work of to make it to make it work. This was the main part. This MCU communicates with the magnetometer via an I2C bus. This is the connection bus and protocol between the MCU and this sensor chip. But controlling the sensor is as simply as read or write register on this sensor device. So it's just two functions, read and write, and you have to know which registers you have to read for what and what meaning do the single bits have, and this is all it's laid down in the data sheet of that BMX 055 device, and it's actually about reading what the what the registers mean, and then use the two functions read and write to to control the sensor. It was, however, indispensable to study also the manufacturer's driver software in this case, because there were undocumented registers that were needed to get the measurements exact, because to compensate for measurement deviations. So the data sheet was only half of the truth, and I had to make my way through a lot of, or not a lot, but some hard digestible C code. And this was the experience. At first, there was frustratingly poor quality of measurements, but I could then get better by these to read out these undocumented registers as the driver did, the C driver, and I could transpose it from that C driver to Rust, and also the calibration step is also necessary to correct the values, and then in the end it really points north as good as it can do. I wouldn't go into the woods with it, but just as a demonstration object, it's enough. So this is the chip itself has reached its end of life already, but it's a combination of three separate devices, and they are still active. So it's still worth having this driver, I think. So I come already to the conclusion. So what has it brought? The outcomes where I have now an adapted board support crate for that Calliope mini board. I have not released it as a crate because, surprisingly, in the same time, a fellow Rustacean has released a crate for it, which is still in a very early stage. But I don't want to interfere with their work for now. And secondly, this HAL driver, I have released it as a crate, but it's still in MVP stage. It's just doing this this compass thing. For me, I found it very instructive to implement this driver for a similar but different device, because I could take the structure from that already existing driver and just read different registers and implement that particular stuff that is special for that BMX 055 device. So this helped me a lot, and now I feel confident to make further steps also, because I'm quite happy with what I've gained so much, and feel motivated. However, what I didn't expect at first, I was forced to read and understand a lot of C++ code. I actually wanted to create something in Rust, and was in the first steps I was I had to turn back to C++, but just for reading. But still, I had to understand a lot about how this software works. Yeah, so far from me. This is my contact, my Mastodon handle, and yeah, thank you for having me here.
Thank you so much for your talk. Very, very cool. Inspired me to also get a little like microcontroller and play around with it. Do we have any questions for Alexander?
Yeah, curious why you chose the compass. How did that project kind of come into your head?
The compass, just because it was, yeah, it was one of the more interesting chapters of this discovery book. So this, yeah, one of the main exercises, basically. Yeah.
Awesome.
More questions. We have time for one more question. Are you looking for contributors to your crate, or do you look for people to help out, like with your driver, like for the crate you released?
I haven't thought so much, but of course it would be nice, yeah, if anybody feels inclined to it. But yeah, as I pointed out, I think it's a very yeah, it's a special yeah, a special area where I was forced to read a lot of C code also, so it's somehow yeah, you have to be inclined to do that also.
Okay, well, thank you so much.
Thank you.
Thanks for taking like your time, and feel free to go to bed now. Like you don't have to stay for the rest of the meetup. It's midnight. Okay, we have the second talk. We have Michael talking about category theory in Rust. I think we don't need a break yet. Or do people feel like they need a 2-minute break to do something? If not, I would just hand it over to Michael. And afterwards, like, we can have a little bathroom break. Okay, so Michael, take it away.
Thank you for introduction. So my name is Michael. I have a whole bunch of experience in Rust. Before that, I was writing a lot of Haskell, so I gained a lot of knowledge in category theory and all the interesting abstractions you have to use in Haskell to get anything done. So turns out those abstractions can also be useful in Rust as well. So first of all, what is category theory? Category theory is a relatively recent branch of math that talks about composition and abstractions. In fact, if you search for abstract nonsense on Wikipedia, up until recently, it was direct link to category theory article. At the moment, it's just a separate page, but it refers to category theory as well. So main two objects in category theory are objects and arrows. So on the graph, I have a simple category containing 3 objects, X, Y, and Z, and 2 arrows, F and G, and 1 arrow that is composition of our arrows F and G. So to have a valid category, you also need to have identity arrows, so arrows that point from the object to itself. But I couldn't find a ready-made slide. This one is taken from Wikipedia. It doesn't have identities. So one of the properties to have a valid category, composition of arrows must be associative. In Rust, it's usually valid by the types. So for example, here I have for different concrete types, A, B, C, and D. And that's objects. I have 3 different functions, F, G, and H, that connect different types. And we can compose them in different order. First compose in F and G, then compose in H at the beginning, or we can compose G and F and append H. So this equation must hold. In Rust, for categories, you usually use concrete types in your API. If you work with a type state pattern, the objects can be different type states. And it allows to nicely visualize possible state transitions. Like you create that database handle that is not connected, then you have transition to connected state and back, and this gets nice visualization. So next interesting abstraction is called a functor. So if we have a category with objects and we can map every object and every morphism to some other category, then we have a functor. This sounds very abstract, but in practice there is several functors even in Rust, and I'm pretty sure you use them. So option, result, vector are all examples of functors. And knowing if something is a functor gets you some practical applications. For example, since functor maps every morphism in one category, the morphism in a different category, and all the compositions must hold, you can easily see why optimization like this is valid. So if you have an option and you have 2 different functions, F and G, that change values in this option, you can either apply them separately or you can apply them both at once. It doesn't make much difference in case of option, but if you have a vector, changing it with the composition of functions will save you on the traversal time. So functors usually collections of some sort. So it's, as I said, it's a result vector. It's values of hash map, values of BT3 map. Most of the collection where value doesn't affect the shape of the collection is a valid functor. But you don't have to have a collection to have a functor. For example, here I have an abstraction called reader. I start with a boxed function that goes from unit to itself. Then I can apply transformation to that boxed value. So something that functors allows you to do. And at the end, I can execute this functor. So typical example of such functor is a parser. Like if you ever used num, data type of num parsers in num look something like this. If you expand type aliases, you have the input function returns the result of parsed value and leftovers, or it returns the error. Just the abstraction of functor itself doesn't let you decompose them. For that, category theory gets one more interesting abstraction called applicative. So applicative, if you have a functor with value a inside and the same functor with value b inside, you get a functor of pair. So again, in Rust, those are option zip and result zip. So parsers are also applicative, and you can implement something like that. And if trade parser handles the propagation of the input to the output, you can write something that is easy to compose, but you don't have to think of propagating the input yourself. So overall, category theory gets you ability to get higher level overview of your application or API that exposed to the users. It allows you to write composable code. And if you compose, for example, in terms of applicative functors, suppose you have 10 objects, simply by composing them with naive functions, you have 100 possible composition. But if you describe their composition in terms of applicative or other abstractions in category theory, you just need to prove that the laws of applicative hold for every object. And instead of n square, you just need to think about n possible combinations. And the best part, users don't have to know anything about it. So to give an example, I made a command line option parser that uses applicative abstractions. So here I can create a separate object that corresponds to width, height, and so on. I can compose them using construct macro. And this gets relatively readable code. And the parser works, parses command line options, generates error messages. So if you want to know more, I have an article in Rust magazine where I cover more steps where I create this parser. There is Wikipedia article on category theory itself. From here you can find a lot more. There is a library I've been talking about. There is a whole bunch of users already. And you can find me on the GitHub and Mastodon. I guess that's about it. Now, if you have any questions.
Yeah, this was very, very cool. I can also highly recommend to read like the Rust magazine article. Like it goes a little bit more in depth. So it's it's a very fascinating read. Any questions? I have a question, like where do you see like it's quite like an abstract or like a sophisticated way of like writing code. Like where do you see it like applicable in your day-to-day? Or like do you use category theory thinking in your code base, or have you helped code bases integrated?
It helps a lot. So category theory is a whole bunch of separate small ideas. And once you recognize how to spot those patterns, you no longer see this is a huge data type, there is 100 methods. No, this is applicative functor. There is just 2 operations you can perform. And there is a whole bunch of operations that's valid for all the applicative functors. As an example, I was working on implementing a parser that must parse serialized schema and then generate parser for that on runtime. And at first it was very difficult to figure out how everything must fit together. But then I decided to think about what exact operations I need. And I was able to break it down like 3 different patterns. It was free applicative, it was monad operation here, and it was alternative operation there. And from that, I was able just to sit and write down the code, and it worked first try. So it's about recognizing patterns. It's about thinking of your code. Often you use category theory abstraction in Rust. So question mark operator, for example, that's valid for option and result. It's a monadic bind operator. And then it's a monadic bind operator. A lot of things in Rust are valid in category theory as well.
And do you have a book or some like recommendation to read some of the theory behind? Feel free to post the link in the chat.
Yep, I will. So there is category theory for programmers by Bartosz Milewski. And this one.
Okay, cool. I'm gonna check this out. Okay, if there are not any more questions, thank you so much.
Can I ask a question?
Sure, yeah.
Absolutely.
It's been a long time since I looked at any category theory, and I didn't understand it very well at the time. And I'm just learning Rust, but you think of some sort of functor relationship between traits and functions maybe, and types and functions?
Well, I think types can be objects and functions can be morphisms. And as long as you stick to const functions, they even compose as you would expect from category theory. So there is no side effects, for example.
Okay, thank you.
You're welcome.
Any more questions? If not, I would say we take a 5-minute break and then we go to Josh. So people can go to a bathroom, can have a sip of water, refresh their brain a little bit after category theory. And then we can hear Josh talk about graphics. Okay, so let's say 8 or at the full hour, so 6 minutes we're back. Thank you. Okay, we are back for the last talk of the day. Hope people are fresh and ready to hear Josh talk about graphics and Rust. Go ahead, Josh, and share the screen.
Okay, they should be able to see my screen now. Okay.
Yeah, we can.
Okay. Yeah. So I'm Josh Groves. So I'm not in Halifax, but I'm in Newfoundland. So I'm pretty close to Halifax, and that's in my username there. The NL stands for Newfoundland and Labrador. So pretty proud to be from Newfoundland. So I'm going to talk about a quick intro to Rust graphics and some of the ecosystem that's out there. Like I said, I'm Josh Groves, and I'm one of the co-founders and the CTO at a company called Pod2. So we're a smaller startup, and we do both consulting and technology. And part of our technology side is building software, and a lot of that software happens to be using Rust. And so I'll briefly mention how we're using that throughout the slide or throughout the presentation. But yeah, basically trying to make full use of Rust wherever we can, because we're huge fans. So when you start off with graphics, a lot of people kind of ask, well, why do I even care about graphics? What is it that's special about graphics? Why can't I just use my CPU for everything? And if you look at this graph, there was another presentation somebody gave, and I thought this graph was fantastic. But this basically shows how CPUs have evolved over time. So, early on, we were getting pretty huge returns every year. So if your program was slow, you could almost just wait a couple of years and it would magically get a lot faster. And that trend continued for a very long time. But if you look at the far right here, things are starting to level off a bit. So, the frequency stopped going up a pretty long time ago. And so that was kind of replaced by the number of cores going up in your CPU. And so everything is getting multi-threaded now. But ultimately, there are some things that are still not set up well to just multi-thread across a few big logical cores. And so the real important thing here is if your program is single-threaded, then you're kind of running into it looks like a horizontal asymptote here. You really aren't getting big gains every year anymore. So you can't just rely on new CPUs coming out that are just going to magically make your program faster. And so with that, you really need to figure out if you need to make your program fast, can it run in parallel? And if it can run in parallel, what are the options to make it run really fast in parallel? And so that's where GPUs come in. And so, yeah, this is pointing to it, and it's really obvious from the right here how it is slowing down. But first, before we talk about how GPUs relate to this, I want to mention some history. So, wherever you live, I'm sure there's an analog. In Canada, it was Future Shop. In the US, Best Buy. But you'd walk down these aisles back years ago, and you had all these really colorful box art containing these graphics cards. They stopped making these really bright box art for some reason, but you probably remember this if you ever walked through a computer store, even like a decade ago. But the real problem is back in the 1990s, a lot of the early 3D games, they were trying to run calculations on the CPU. So the idea is that you have like a full screen game, and for every pixel on screen, so whatever your resolution was at the time, it could be 320 or 640 by 480 or something like that. But even running calculations per pixel for that many pixels and trying to keep it running at a reasonable frame rate, it was very, very hard. The calculations weren't really complicated. It's just doing a little bit of number crunching per pixel. Is just the amount of pixels that you have on screen at any time. It's just a huge number, and you're trying to run these at real-time speed. So, the lower bar today is running at 30 frames per second, or ideally 60 frames per second, or some monitors really want you to run 144 frames per second, or things are getting pretty fast, and that doesn't give you a lot of time to be running that many calculations. So in response to that, hardware manufacturers basically realize that, hey, this is a big opportunity to accelerate things. So maybe we can develop special hardware that satisfies that use case. So you basically just want to run a lot of simple calculations per pixel. So let's make hardware that can do that. And so that's exactly what GPUs do. So people created these things called graphical processing units, or GPUs. And how they work is, like on the screenshot from Diablo 2, if I blow this up, you can imagine you have this giant grid of pixels. And so for every one of these pixels, it's exactly like I was saying. You want to calculate a color per pixel. And so it's taking into account any kind of effects that you want to apply, what textures or images should be applied to each pixel based on what's going on at that time, lighting, shadows, and all of that kind of stuff that needs to happen every frame per pixel. And so GPUs have been developed to be incredibly fast at running lots of these simple calculations in parallel. And I have simple in double quotes here. They're not necessarily simple, it's just simple enough that you can run them in parallel extremely quickly, as opposed to a CPU that's good at running really complex calculations. So CPUs are good at running fewer calculations in parallel, but they can be very complicated, and GPUs are kind of the opposite. So they excel at doing simpler calculations, but a huge amount of them in parallel, rather than like 16 cores on some CPUs. And so the example here, this is using graphics acceleration, but you can do the same thing for compute too. And so when people talk about doing machine learning on a GPU, it's exactly this kind of thing. It's just, instead of calculating pixels, you're calculating some kind of ML model, but you're doing the exact same process, running a huge amount of simple calculations in parallel. And so that all sounds great, but how do you actually use it from Rust? So if you go and just Google it and you say, how do I use a graphics API? You'll get everybody's opinions of, this is the best graphics API out there, so you should just use this one, and then this one's old and outdated. And there are platform-specific APIs. So kind of going from left to right here. So OpenGL, WebGL, OpenGL ES, these were kind of the standard for a long time. These are produced by a group called the Kronos Group. They're considered a bit old and clunky, but they work really well. There's a huge amount of content out there written about them for examples and tutorials and things like that. So they're very popular. They're not as loved as they used to be, but still very common. Then you have APIs like Metal, which is Apple specific. So if you're targeting Mac OS or iOS, Apple really kind of forces you to go through Metal. And Windows has the same kind of concept with DirectX. And then we have another Kronos Group standard called Vulkan, which is kind of like a replacement for OpenGL, but it's a lot lower level. Then there's WebGPU, which is an effort from browser implementers. They're trying to create a standard modern graphics API for the browser. And then we have these compute-specific APIs. So OpenCL, CUDA from NVIDIA. AMD has their own called ROCm, and there are a lot of different APIs out there. So there's, because of that, it can be kind of confusing trying to get into it first. And so from Rust, though, you can basically choose any of these. And so there's a crate for basically any graphics API you want to use. Somebody has written bindings for them. So I created one for OpenGL, so that's called Glow. Maintain one for Metal 2. There's a standard Windows crate that just has every single Windows API that exists. So that's one way to call DirectX. For Vulkan, there's one called Ash. For WebGPU, there's a really popular crate called WGPU that I'm also maintainer of. Then for the compute APIs, there's also bindings. So you can use any of these. there are trade-offs for each one of them. So obviously the platform specific APIs only work on that platform. So, if you're using Linux, then you're not going to use the Windows the right DirectX graphics, because you just can't really, or you can technically by emulation, but you don't want to do that generally. So what I recommend is, a lot of people, the easiest path right now is to just start with WGPU if you're not sure. And then that gives you a good on-ramp to learning more about all the other APIs in the ecosystem. If you are interested in going on a deeper dive on some of these, if you want to pick up existing OpenGL content, and that's totally great too. And so then you could use something like Glow. So there's all kinds of different options, but if you want to start with something that gives you a good on-ramp, then I'd definitely recommend WGPU. And so the way you'd start with any of these graphics APIs is that they're structured so that they want to batch things up and send it to your driver. So if you can imagine making a slow network call or something like that, it kind of works the same way. You don't want it to be chatty all the time. So the idea is that you create a bunch of commands and then submit them somewhere for processing. And so how that actually looks is, this is kind of pseudocode, but this is the basic idea that you'd see in any of these APIs. So you start by accessing the GPU. And so this is actually making a connection to the driver and saying, hey, I'm about to start rendering or computing some things. I need to open a connection with the driver. So after you do that, then you write a program that's specialized for the GPU and called a shader. And that's actually what runs on the GPU. So like I mentioned earlier, if you're doing compute, this could be like a ML specific compute shader that knows exactly how to calculate matrices for the problem that you want to work on, or if it's inference, exactly how to set the problem up. If it's rendering graphics, then this is describing what kind of lighting effects you want to apply, and how do you want to transform your geometry and those kinds of things. And next, that's where you get into setting up all of the inputs to your GPU. So like I said, you want to record a batch of commands all at once. So the commands are things like, I have this really cool 3D model and I just want to upload that to the GPU. And then afterwards, I want to add lighting effects to the model and make sure I can draw shadows because I want to display it in 3D. And so you record all of the commands, and these can be, you can have a lot of commands. So, a lot of modern 3D games might have tens of thousands of commands that they're recording into these. And then after you do all that, you actually submit it to the GPU. So you say, here, I have this big serialized encoded set of commands, and I just want to submit it to the driver, and then it's up to the driver to figure out how to deal with that. So the driver will figure out how to schedule them based on dependencies between the commands and different things like that. And then eventually, if you're rendering graphics, then it'll display it on screen somewhere probably, or if you're computing things, then it might write the result somewhere so that you can access it and then read it back onto the CPU. Shaders are a really important part of the graphics API, so I just wanted to call them out specifically here because a lot of people get tripped up on this. But they're not actually that complicated. It's just like any other programming language, except they're running, you're not running them on the CPU, you're running them on the GPU, but they really look the same as any other CPU program. So the first important shader type is called a vertex shader. And so these are used to position triangles that will be rendered on your screen. And so if you look across this diagram here, so we start with a bunch of vertices. So if you download a 3D model from somewhere, a lot of them are just described as a bunch of different points in 3D space. And so a vertex shader takes in those points and transforms them into a series of triangles that you're going to put on screen somewhere. And how that actually looks in a programming language. So this is a shader language called Wigzil for web GPU shading language. There are a lot of other shading languages, and I don't have enough time to talk about them all here. But you basically just want to use whatever shading language works well with the graphics API that you're using. So in Wigzil, it kind of looks like Rust. So, you have a main function and you're saying, I'm going to grab the position from that 3D model and then project it into a 2D representation. And that's what's actually going to be shown on screen. So you're just creating a bunch of triangles. So they don't have to be as complicated as people sometimes make it out to seem. And then after you have your triangles, GPU says, okay, I know exactly how to render a triangle. So I'm going to figure out how many pixels should be shown on screen for each one of those triangles. And then the next type of shader is called a fragment shader. So all fragment shaders do is they iterate through each one of these pixels and they say, what color should I show for each one of these pixels? And so how that actually looks, it's almost the same as a vertex shader. So you can see instead of vertex, we have fragment here. And we're writing out the color that we want to show per pixel, basically. So this one just writes the color red because it's RGBA, so red, green, blue, alpha. So this can be as simple or as complicated as you want it to be. If you wanted to make it a gradient, like it is shown here, then the GPU actually does interpolation for you and all kinds of fancy things. But if you wanted to just write a color like red, then you could do that too. Or if you wanted to get into more complicated things like lighting and shadows and everything, like I mentioned earlier, then you would include that all in your fragment shader. And then the GPU is responsible for blending things together and doing all kinds of other stuff after this. But at the end of the day, it'll present this somewhere. So if you're presenting it to an actual surface attached to a window somewhere, then you would see all those colors on your triangles on screen at some point after. And like I mentioned earlier, so compute shaders are also, so we have vertex shaders and fragment shaders for rendering graphics. And then for using just compute, just pure calculations, we have dedicated compute shaders for those. So they're general purpose, which means your GPU doesn't really have specialized hardware like it does for rendering. So it's not doing these fancy rasterization and blending steps. But compute shaders are really nice in another way because they're just arbitrary programs. So just like you write any kind of program on your CPU, compute shaders work the same way. And so this is a really simple compute shader that just multiplies everything that you're sending in by 2. So again, these things can be as simple as you want. If you just want to multiply a very big list of numbers by 2, then you could do it like this. In practice, this will be a lot more complicated. So you're going to do some kind of fancy calculation in here. Like I mentioned, if you're doing ML inference on the GPU, then you'll put the entire calculation in here, and that's where it sits. And then, so I wanted to show a little bit more about the WGPU ecosystem, because I think understanding how some of the crates relate to each other can be interesting too. So in WGPU, it's not actually talking to the driver directly. It's using one of the bindings I was showing earlier to talk to your actual graphics hardware. So way down at the bottom, we have things like Glow and the DirectX bindings, Metal and Ash for communicating with the Vulkan API. So these all talk to your actual graphics hardware. And then just like the embedded systems, how that Alex mentioned earlier, there's the same kind of concept here, in that we have hardware abstraction layer that knows how to talk to each one of these different graphics APIs. And then way up at the top, that's the actual entry point. So if you wanted to use WGPU as, just a regular application that wants to import it as a regular crate, then that's where you would import it. And lots of game engines, applications, games are all using WGPU directly like that. And by doing that, you can use it for both desktop applications or web applications. So for web applications, you can compile it down to WebAssembly and use it in your browser. Or with desktop applications, then it'll work the same as if you were using any of these graphics APIs directly. except you just have one API to worry about, and it'll handle all the platform compatibility and portability for you. So you can write one graphics application that works on Mac OS, Windows, Linux, basically anywhere you can run typical graphics hardware. Another interesting point about WGPU is that it's actually used, the internals of it are actually used as part of Firefox for the implementation of the WebGPU API. So that's kind of interesting, because if you compile your program down to WebAssembly, you can run it in Firefox, and then in turn, Firefox is running WGPU internally to talk to the graphics hardware. So it's kind of a weird thing, but yeah, there's a lot of benefits to this whole ecosystem, and it's done really well in the Rust community because of that. And so, people often ask, well, who actually uses Rust graphics and creates like these? And there's all kinds of different things. And so you see a lot of games here. A lot of fantastic games have been released, and this one came out in December, actually, at the top right. But there's all kinds of different things out there, and they're all very impressive. But beyond games, there's actual game engines that work directly on top of this. We have things like Ruffle, which are that's a Flash emulator that I think I read the other day that it's actually being used for some of the old New York Times articles to replace all their Flash content. And we have things like UI libraries. So we have things like ICE that provide component libraries that you can create your own GUI directly in Rust without involving any other stack, which is really cool. So this is running directly on top of the GPU. There are code editors that are writing directly again to the GPU rather than trying to do any kind of rendering on the CPU. My company, Pod2, we're using WGPU to render this kind of schedule view, kind of like a Gantt chart, but doing some pretty cool stuff that we wouldn't have been able to do if we tried to use some of the other technology that's popular for that. So doing CPU rendering, or using like a typical web stack. So there are all kinds of different use cases. So it's very cool. And if you haven't seen this side of Rust, I definitely recommend. There are a bunch of lists that list some of the projects like these, but definitely recommend checking it out and playing around with the examples out there, because they're very impressive. And so I wanted to show really quickly some examples here. So if you go on to the WGPU website, there's an examples page that just shows some of what's possible. They're mostly meant for showcasing how you might use some functionality in WGPU. But even clicking through some of the examples, you can run these in your browser live. And so this is running right against like the web GPU implementation in Chrome. But this is a Rust program compiled down to WebAssembly and running in your browser. The Bevy game engine has a huge examples page, which is really fun to play with. And so there's an example here, same concept. So this is something a little bit more complicated, so you can see real-time lighting and shadows, 3D objects, and how they all interact with each other. But all of this stuff, it's just super impressive just to play around with some of these examples and see what's possible today using a mostly Rust stack. A lot of these stacks are like 90% Rust, so it's very impressive. So it's kind of like Rust all the way down to right above the graphics driver, and maybe we'll get Rust in there eventually too. But that's all for my talk. So thanks for listening. I'm super passionate about graphics and Rust, so happy to talk to anybody that's interested in these more anytime. I've been in this whole Rust graphics ecosystem since about 2017, when I was just trying to draw like a few rectangles on screen, and I really haven't left it since then.
Yeah, thank you. Super cool stuff. Do we have any questions for Josh?
Yeah, I got one. So you were showing with your company, you're doing that Gantt chart looking thing. And like, so if I was going to build that, I would like try to do it in React or something. I'm just curious if you could elaborate a bit more on like why that's useful for that application or whatever.
Yeah, and so we do use React for a lot of the other UI in the application, but for that schedule view specifically, trying to use React for that when you because for us we're really interested in showing like a huge number of rectangles on screen all at once, and trying to be totally smooth as you zoom all the way out and zoom back in and jump around. So there's a lot of detail that we wanted to show on screen all at once without being limited, and so it's possible to do some of that in React, but you kind of end up turning off a lot of the convenience features in React by doing that. I've done something previously using React or using just like a HTML canvas directly, or some people do it with SVGs and things like that. But at some point, it varies. But when you start to get into thousands of nodes, usually the performance starts falling off. So the performance is probably the biggest point, but trying to do some of the custom visualization stuff that we have on top of that schedule view was also really important. So we have real-time graphs that are associated with the different activities that you see in the schedule, and things like that. So that's the biggest reason. There are a lot of fantastic React Gantt charts out there too, but yeah, it's more of like a performance and being able to use one stack for all parts of it rather than using React for a fraction of it and then using Canvas for parts and things like that.
Cool. Well, I learned a ton from your presentation, so thank you.
Awesome.
More questions? Anyone? I have one. Like, what would you say, like, if someone wants to start, like, what is a good project or a good framework or a good part of the framework to use?
I think it depends what you want to build. So if you wanted to start developing a game, for example, I think Bevy is probably like the number one choice as an entry point for that. There are a few others. So like I know MacroQuad is pretty popular for getting like a really simple game going. And I think their focus is more on 2D, but Bevy is more specialized towards 3D. So games, you have options like that, and then you have bindings to all the typical stuff out there like Godot and some of the other game engines. There's Rust bindings to all that stuff too. I didn't cover that in the talk, but there's bindings to pretty much anything that you possibly want to make a game in. So all those exist, but if you wanted to do just like specialized graphics or specialized compute, I think right now the easiest entry point is WGPU, just because it takes care of all the portability for you. So you don't have to worry about, well, what happens if I have a MacBook and I start developing my program based on Metal, and then I buy a new Windows laptop and I have to start over basically. So using something like WGPU allows you to not worry too much about that. There are other options that are more portable than Metal, but not as portable as WGPU. So like Vulkan, for example, there's a Vulkan implementation called Molten VK that does run on macOS. But the problem with some of those too is like Vulkan is especially low level. So if you're coming into graphics without prior experience, it's nice to have something that's not really high level, but a little bit more high level like WGPU, because you don't have to worry about as much of the boilerplate that exists in Vulkan, which, at some point maybe you want that stuff for performance, but I wouldn't recommend starting there just because there are a lot of concepts to pick up.
Mm-hmm. I can imagine. Okay, cool. Lots of new things to look into after this 3 talks: graphics, microcontrollers. Nice, cool stuff. Okay, folks, this was it for tonight. Thank you for joining. Thank you again for the 3 speakers. These were super interesting talks. I try to upload the talks or like the whole like meetup like later tonight. I can send out the link on the meetup like event comment section. For next time, maybe think about to give a talk. I plan to do this maybe like once a month, maybe like little somethings in between. If someone has like an event idea, feel free to like approach me. There is a thing called Hack and Learn in Berlin where people like meet like once a month and hack together on a project. Maybe that's something like we want to do here too. But yeah, let's see where this meetup is bringing us. So thank you so much for coming and see you next time. Take care.
Awesome. Thank you.
Bye.
Thanks to you.